everyone, I wanted to make a short video that shows you some of the cool ways you can use the big three along with gravity to get some interesting information in a way that might feel a little more efficient than how you might initially think to do it. So here's what seems like a pretty simple problem. I have an object on the side of a cliff. It's above some water. That object is thrown up at a speed of 7 meters per second. And we know it's going to travel up for a little while, briefly stop at the top where its velocity is momentarily going to be 0, and then it's going to come back down. And as it comes back down, it's going to have some impact velocity, I'm just going to call v, that's with which it's going to strike the water. Now, a lot of times when you get asked for impact velocity or the speed with which it strikes the ground or something like that, what happens is you might want to say, oh, it's 0, right? Because after it hits the ground, it's clearly not moving. But whenever we ask for impact velocity in physics, we mean the speed with which it hits the ground, just before it hits, like that very last fastest speed it gets to. That's important to keep in mind. And so I could ask for a lot of things in this problem. I could ask for how high it gets. I could ask for, how long it takes to get to the top. I could ask for all kinds of stuff. But I'm just going to ask for the impact velocity. What speed does this stone or object or whatever it is strike the water with? Okay. And let's see if we can be super efficient, because a lot of people do this problem. The first thing that they do is they try to divide it up in a lot of ways. So they divide it up. And they say, well, first I got to figure out how long it takes to get to the top, and then I got to figure out how long it's going to take to hit the ground, and then I've got to figure out how fast it's moving when it hits the ground, because it seems like this should be divided up into a couple of different phases. But one important thing to remember is that throughout this entire trip, whether you're on your way up or whether you're on your way down, the acceleration is negative g. And let's just remind ourselves of what's going on there. As you travel up, your velocity is upwards. The acceleration is pointing down because it relates to the force of gravity, which always pulls down. Gravity never acts up. And that downwards acceleration works against the upwards positive velocity, and it's going to slow you down. When the velocity switches direction and points down, the acceleration is also pointing down. The two of them work together, and they actually speed you up. And so even though on the one hand you're speeding up and the other hand you're slowing down, the acceleration's direction is not changing. It's just the direction of the velocity relative to the acceleration. Okay, so now that we know the acceleration is the same whether I'm going up or down, I'm going to define an upwards direction as positive. Now, you don't always have to do that, and sometimes defining downwards as positive is actually even, more convenient. But when you're moving both up and down in a problem, I generally default to choosing up as positive. The other thing you want to do is define a height equals 0. Now, you can call height equals 0 the top of the cliff where you're starting. I always like to call height equals 0 the sort of bottom of my coordinate system, the lowest point reached in the problem. So in this case, I'm going to choose the real ground to be height equals 0. And I want to get this final velocity. Let's see if I could do this with one equation in one step. Let's make a list of our variables from the big three. So my my initial position, I'm starting up here on the cliff, is going to be 10 meters, positive 10 meters, because I'm 10 meters above the height equals 0 mark. My x final, when I get down here and I hit the ground, is going to be 0. My acceleration I know is negative g, or negative 9.8 meters per second squared, and that's because gravity always points down, and I've defined up as positive, so now the acceleration is down, which means it would be negative. My v initial back here is positive 7 meters per second. If I had instead thrown it down, that would be negative 7 meters per second, because it would be moving in the down direction instead of the up direction. My v final, which is when it hits the ground, I don't know what it is. And time, I don't know, but I don't care. So given that I don't care about time, we want to think about which equation doesn't have time, and if you remember, it's this one. The one that doesn't have time. So let's plug in all of our numbers. So v final squared is what we want. V initial squared is 7 meters per second squared, plus 2 times a, which is negative 9.8 meters per second squared, times x final, which is 0, and it's really important you get the order right here, minus x initial, which is 10 meters. And so I get v final squared equals 49, and then minus 2 times 9.8 is 19.6, times 10 is 196, and a minus minus is a plus 196. And I get v final squared is 49 plus 196, 245. Now, here's what's interesting. You think, okay, I'm going to take the square root of both sides to get v final, which I indeed am going to do, and I get 15.7. But remember, when you take the square root, you always get a plus or minus. And so in this case, since we know the final velocity is moving down, according to our coordinate system, our final velocity is actually negative. So in physics, you've got to pay attention to those little things. So our v final, the impact velocity, is negative 15.7 meters per second. Hope that was helpful. See you later. Bye.